So the empirical rule of normal distributions, as the name suggests, it is for a normal distribution. Now you may say, well, what is this normal distribution that we're talking about? Or, what could it be? We've seen this before. A distribution that is symmetric, clearly isn't. Oh. Wow, usually I'm good at drawing the bell curve, but something's off. Oh. Well, that is good enough. So that is a symmetric distribution. In the sense, as you can see, that both sides are opposites or mirrors of each other. Pardon my artistic talents. The iPad, I couldn't draw it properly, but if you look at a bell curve, it would be symmetric. And we know that it has no skew. And we also know that the mean would be approximately equal to the mode, which should be approximately equal to the median. We did a problem like this last time. One of the problems, I think the old faithful problem in the measures of center video, it didn't look exactly normal, but it sort of had an outline bell curve, so that we can approximate it using a normal distribution. So on the data axis, that point right there is the mode, because that corresponds to the highest point of the curve, which is the highest frequency. Since we know for a symmetric distribution, the normal distribution, mean is approximately equal to the mode, which is approximately equal to the median, that center point would be the same as the mean as well as the median. Now, what we know about the median is that median splits the data exactly in half. And specifically, when we say data, we're talking about sorted data. So here we have the real number line, and by default, the numbers here are all sorted. The real number line is a sorted line, goes from lowest value to the highest value. So naturally, we have an ordering when it comes to the numbers on the real number line. So now that I know the central point is the median, what I know is that the data, 50% of it would lie over here, and 50% would lie over there. So 50% of all the data would lie below the median, so in that area, and 50% would lie over there. Now, you may say, well, what is the connection between the bumpy curve and the observations that we see? The more observations I have over here, the more area I will have under the curve. So, for instance, So think of each dot that I'm going to put as an observation, but I'm piling it on top of each other so that you can see the outline. But each dot means a number on the real number line. So I have more observations on one side. And now I have the exact same number of observations, or nearly the same, on the other side. So those observations fall on the real number line, and I'm piling it up. So that gives me this nice little bell curve that I was trying to achieve. So that's what we mean by 50% of the data on the left-hand side and 50% of the data on the right-hand side. And clearly, the area under the curve that I drew, that area determines the percent of points below a specific observation on the real number line. So from the looks of it, we can see that more observations are concentrated right in the middle. And as we go farther and farther away, the observations kind of thin out or dwindle. So that idea is what's captured by the empirical rule. So we know the mean, the median, and the mode, they are approximately equal to each other. So and we know from above, 50% of the observations would lie below the median, and 50% of the observations would lie above the median. Now, I want to go one step on either side of the mean by one standard deviation. So I want to go one standard deviation to the right and one standard deviation to the left. And according to the empirical rule, the percent of observations between those 2 points is 68%. So that's what the rule suggests. So if I drew a bell curve between those 2 points, I will have 68% of the data. So just by knowing the mean and the standard deviation, we can say what percent of data observations would lie between the first standard deviation on either side of the mean. In a similar manner, if I went 2 standard deviations from the mean, I'm going to have 95% of the data, and you can see the shape or the area increase as I keep on increasing the standard deviation. So you can see the curve develop. So now we have 95% of the data between two standard deviations. And if I went 3 standard deviations from the mean, I will end up having 99.99% of the data, but not 100%. Of course, there could be 1 or 2 on either side. Those would be the outliers. So 99% of the data would lie within 3 standard deviations of or from the mean. So if we know that the data is bell-shaped in the sense it is symmetric, we can say that 68% of all the observations would lie between x bar minus s and x bar plus s, where s is the standard deviation and x bar is the mean. The more observations you have on an interval, the denser the area is going to be. That's why in the first graph, the middle part is shaded. Now, if I expand it to 2 standard deviations on either side of the mean, I increase the area under the curve, it becomes 95%. If I went 3 standard deviations away from the mean on either side, that has to be a negative, then 99.7% of the data would lie between x bar minus 3s and x bar plus 3s. One may ask, well, what if I just went from negative infinity to positive infinity? What would be the area under the curve? It'll be 100%. So if you have a data like this, and even if you went 100 deviations on either side and you wanted to find the area, that area is going to be 100%. So you have to keep the note in mind. Area under the entire curve is 100%. So for instance, don't even have to be 100. I don't want to confuse you. Let's just say 80 standard deviations on either side. So if you said just for fun, oh, I'm going to go 80 standard deviations on the left, 80 standard deviations on the right, what percent of data is going to lie between those two values? 100%. In other words, all data observations will lie within those two points. So here is the data on the Old Faithful geyser in Calistoga, California. This is something that we did with measures of center. If you recall, I'll just go back to that particular problem from the last section. We found the mean and median, we defined class width, and we ended up getting a funky looking shape. And if you go back, I did say, well, it doesn't look exactly normal, but I could make an observation that this is, make an assumption that this is normal. In other words, it's symmetric. It's not perfect, but it's almost symmetric. If we adjust the class width, perhaps we can see symmetricity in a better way. So the problem now wants to find the sample standard deviation, and they want we could simply use the calculator to come up with an answer. So first we've got to enter the data. So now it's a 9. So I have the data in. We can actually create a histogram just to see the shape of this data. So press second start plot, turn it on, and go over to histogram and the data in the list, which is list 1. And we have to adjust the window because the values are in the hundreds. So we can go from 80 to 120 or 125, 0 to 10. So that's the graph we get. And you can see that it is sort of a bell curve. It's not perfect, but if you kind of did an outline, it would look like a bell curve. So the data is approximately normal. In real life, most data sets would look much more nicer than this one, and you can clearly pick out the shape of the distribution, if it is a bell curve or otherwise. So we need to find the standard deviation. So go to statistics and one more starts, list one, and we have the mean, 104.13. The standard deviation is 6.24. That's what we had previously. I think so, but yes, it's 104.14. So we can round it and call it 14. And they want us to round it to the nearest whole number. So I'm going to round the mean to 104, standard deviation to 6. The nearest whole number is 6. And there are 44 observations. So part B, from the histogram, we see that the data is approximately normal in the sense the data is approximately symmetric. And the mean and the mode would be approximately equal to be mean, median, and mode would be approximately equal. In this case, we saw already that the mean is approximately 104, and the median is 104. And the median happens to be a whole number because the data is simply whole numbers. So the median is just 104. So now we want to find or use the empirical rule to determine the percentage of eruptions that last between 92 and 116 seconds. In other words, if we determine how many standard deviations each of these data points are, then we can determine the percent of eruptions that last between 92 and 116 seconds. So the mean is right over there, and 116 is right there, and 92 is right there. Our objective is to find the percent that lies between those two values. In a problem like this, if it is empirical rule, those points, the endpoints that we have should fall into the strict conditions of the empirical rule, in the sense within 1 standard deviation, within 2 standard deviation, within 3 standard deviations, and so forth. So I am going to determine the number of standard deviations. 92 is from 104. So I'll simply say x bar minus k times s is 92. So from the mean, I took a few steps. So that's why I have a negative k times s, and that happens to be 92. So if I plug in 104 minus k times the standard deviation is 6 equals 92, which would mean 6k equals 104 minus 92. 6k is 12, so k is 2. So if I get 2 for the left-hand side, and if I get 2 for the right-hand side, then I know from the empirical rule as to what percent of observations would lie between 92 and 116. So let's see if x bar plus k times s equals 116, give us the same k. So x bar is 104 plus 6 times k, 6 is the standard deviation, equals 116. 6k would be equal to 116 minus 104, which will be the same as 6k equals 12, and we end up getting k equals 2. So what does this say? This tells us the observation 92 is 2 standard deviations to the left of the mean, 116 is 2 standard deviations to the right of the mean, which would imply that 95% of the observations must be between 92 and 116, because that's what the empirical rule tells us. So the answer here is 95%. That is a fixed number. As long as the data is normal, this rule would always apply. The weight in grams of the pair of kidneys in adult males between the ages of 40 and 49, has a bell-shaped distribution with a mean of 325 grams and a standard deviation of 30 grams. They want to know about 95% of kidney pairs would lie between what weights. The key words here are bell-shaped distribution. The quantities needed are the mean and the standard deviation. So one, it is bell-shaped. In other words, it's normal. Two, the mean is 325 grams. 3, the standard deviation is 30 grams. So first, some wouldn't want to draw the normal curve and jump directly into solving the problems, and some would like to draw the bell curve and then proceed from there. We know if there are 95% of the observations lie between 2 points on a normal distribution, then those 2 points must be 2 standard deviations away from the mean, just like the previous problem. 92 and 116 were 2 standard deviations to the right of the mean. So I like to draw a curve and put the numbers up so that I know as to where the points would lie. So the mean is 325. The standard deviation is 30 grams. So if I go one standard deviation on either side, so over there, it'll be 355. I'm adding 30. Over there, I would have subtracted 330, so I'll have 295. And that area in blue would be 68%. Mind you, this is an approximate graph, not exact. Now, if I went two standard deviations on either side, I need to add another 30 to the previously added 30. So 355 plus 30 is 385. 295 minus 30 is 265. So, and notice this area includes the previously shaded area. That is why we are getting a higher percent. So now we have 95%. And lastly, three standard deviations. So I'm going to go and add 30 to 385. That would bring me to 415. And subtract 30 from 265. That would bring me to 235. So we'll use a different color. Maybe that. So the light orange one covers 99.7% of the area. The orange covers about 95%, and then the brown covers about 68%. So now I know the points corresponding to the mean, one standard deviation to the right of the mean, two standard deviations to the right of mean, three standard deviations to the right of mean. Here, one standard deviation to the left of mean, two standard deviations to the left of mean, and three standard deviations to the left of mean. Part A, about 95% of kidney pass will be between what weights? Clearly, two standard deviation from either side. So we have 265 here and 385. So the answer is it has to be between 365 grams and 385 grams. Now we want to know what percent would lie between 335 and 415 grams. So 235 is right here, 415 right there. So we know 235 is 3 standard deviations to the left of the mean. 415 is 3 standard deviations from the right of the mean. So and if we combine the two observations and use the empirical rule, this simply tells us 99.7% would lie between 235 grams and 385 grams. So if I went around and picked adult males between the age of 40 and 49, 99.7% of them would have a pair of kidneys that weigh between 235 and 385. So this has to be 415 because it's 3 standard deviations on either side. Explain how to do this. So, part C would like to know the percent who would weigh the percentage of kidney pairs that would weigh less than 235 grams or more than 415 grams. So in our reference picture, I know that 235 is right there and 415 is over there. And I also know the percent that lies between those 2 points is 99.7%. And earlier, I mentioned that the area under the entire curve has to be 100%. So if 99.7% lies between those two values, whatever that remains must be on either side. So you have total area, 100%. Minus 99.7%, you get 0.3%. And now if someone asked you, well, what percent lies just above 415? Well, it has to be exactly half of it, so it would be 0.15%, and the same over here, 0.15%. And as you can see, if you add all those values, it would add to 100%. Part D would like to know the percentage of kidney pairs that would weigh between 295 and 385 grams. So I have my reference picture there. So the mean is at 325 and 295, 355, 385, and 265. So I'm putting all those points because I know 295 is right over there and 385 is right over there. So what do I know about 295 and 355? I know 68% lies between those 2 points. What do I know about 265 and 385? I know 95% lies between those 2 points. What else do I know? Well, I know the area, the curve is symmetric. So whatever area that's left over here and there must be the same. So I'll call that x. So 68% plus x would equal 95%. So 68% plus 2x would equal 95%. 2x would be equal to 95% minus 68%. So 2x would be 27%. Divide by 2 on both sides, x is 13.5%. So I know the area here is 13.5%, and there it would be 13.5%. So all I have to do now is to find the area or the percent between 295 and 385. So 68% plus the missing amount, 13.5%, that gives me 81.5%. And that would be the final percent that lies between 295 grams and 385 grams. So here we want to determine which professor is better in teaching introductory biology. There's Professor Alpha and Professor Omega, and I'm going to assume the distribution is symmetric. It doesn't state in the problem, but if we assume so I don't want to make it confusing, because the mean score of 80% and standard deviation of 5%, well, let's drop the percent in the score, because we're talking about percentages and I don't want to add another layer of percentages to that. So it's a mean score out of 100. So I'm just going to say 80 and 80. So Professor Alpha is over here. Professor Omega is over there. And we want to look at within one standard deviation. So 85, 90, 95. Subtract 75, 70, 65. And for Omega, we get one standard deviation, but the standard deviation is 10. So 80 plus 10 is 90. 80 plus 20, 2 standard deviations is 100. And I don't know if Professor Omega is going to give a 110, but we'll just put it over there. And on this side, 70, 60, and 50. So if we look at the curve, we can see 97 or will make a score between 60 and 100 in Professor Omega's class. In Professor Alpha's class, 95% of the students '70 and '90. Well, that doesn't give much of, a solace, I believe, because both of them seem quite reasonable to me. So maybe we've got to look at it from a different perspective. So let's just say the percent above 90 here, and the percent above 90 over there. So if we look at the graph, we have for Professor Omega, 50% of the students score below 80, and then I'm having about 34%, which is half of 68, score between 18 and 90. So I can conclude 16% would score above 90. If we look at Professor Alpha, on the other hand, 97.5% would lie below 90. The reason being 95% is below 70 and 90, which would mean 2.5% has to lie below 70. So according to that, there is a 2.5% chance, or 2.5% of the students would score above 90. So if you want to, if you're a great student, then Professor Alpha's class would be better because you're between 70 and 90, you have a 95% chance of passing and getting 90, between 70 and 90. If you're in Professor Omega's class, there's a 95% chance that you'd make a 60 and 100. But if you're aiming for that A, you have a greater chance with Professor Omega than Professor Alpha. But who's going to be more consistent? Clearly, Professor Alpha is going to be more consistent because the standard deviation is low. It's only 5%. Low standard deviation implies less error and more or better consistency.